chargé de recherche au CNRS University of Rennes, will speak on analytical normal forms for singularity of planar vector fields.
So I would like to present a work that I have just almost finished, and which I think illustrate the strong influence that César Camacho had on my way of thinking mathematics. So I start with to recall three results. So you take a germ of holomorphic vector fields in the plane. So at C2, 0, and with a singular point at 0. So you can look at its linear part. So in the matrix form, you can write it like this, or also like this. And consider the eigenvalues of the linear part. Then the well-known theorem of Poincaré-Dulac. Says that if the eigenvalues are not vanishing and the ratio is not real negative, then either you can linearize the vector field by a local change of coordinates, or possibly, in case, or possibly to the following form: lambda kz plus wk dz plus lambda w dw, in case the eigenvalues are resonant. This means that lambda 1, lambda 2 takes the form lambda k lambda for some k which is positive integer. So when the ratio is negative, you can also find polynomial normal forms, but this is done in the work of Dulac, but with a formal change of coordinates. And then there is a lot of works on the subject which shows that for exceptional values of this ratio, this change of coordinates is almost divergent, almost always divergent. And even we have good reason to think that for those exceptional values, most of the vector fields cannot be transformed into a polynomial normal form by an analytic change of coordinate. So what can we do to simplify the vector field by analytic change of coordinates? So this is the goal of my work. And in this direction, there are two works that I know. One of Ekal, I will talk later about this. And there is a most famous work of Strozina and Zoladek in the nilpotent case. The nilpotent case, it is a case where x1 takes the form 0, 1, 0, 0. In this situation, they proved that the vector field can be transformed by analytic change of coordinate into the following simple form. Or there is another equivalent normal form, which is the following one. W dz plus this normal form is called Bogdanov-Takens normal form. Here is Bogdanov, here is Takens. And Bogdanov and Takens proved that it was possible to put x into the following form by a formal change of coordinate. And the big theorem is the theorem of Strozina-Zoladek. It can be done in an analytic way. And the proof is to consider a special algorithm of successive change of coordinate, and prove that this algorithm is convergent. And you have 20 pages of inequalities to prove this. Corollary. From those normal forms, you can, so this also appears in the paper of Strozina-Zoladek. From those normal forms, you can consider the invariant curve of the foliation, and you have essentially two possibilities. So C is the invariant curve, the separatrix of the foliation, or the vector field, and either C is analytically conjugated to a curve like this, a cusp or a generalized cusp for K equal or okay, and in this case X has an alternate normal form, which is the following. You have an Hamiltonian part first, which is a vector field whose trajectories are given by the level curve of W square minus ZQ, Z to the K, plus a dissipative term like this. Or C is equivalent, is smooth. You have only a smooth invariant curve, and in this case you have another normal form, which is this kind. Okay. Well, those normal forms are not unique. In fact, for instance, in the first case, the cusp case, k equal 1, and when the order of G equal 1 also, then you have a further reduction to of the coefficient G can be further reduced to the following form: G equal Z plus a function of Z to the third. So this means that you can kill two coefficients on 3. But so this is, I have done this several years ago, and this was formal. And there is a work of Canalis and Schafke, where they prove the divergence, the generic divergence of this reduction. Okay. So the third theorem that I want to mention is a theorem of Ekal. So perhaps I write it here. And this is for the case of saddle nodes. So the linear part is like this. And it is a theorem on foliation, not vector field, only foliations. So in this case, the foliation associated to X can be formally reduced by the works of Dulac to a form like this. And you have, from the formal point of view, two invariants. But this is almost always divergent, and Ekal proved the following. In the case, the formal invariant k and lambda are 1 and 0, then the foliation is analytically equivalent to the foliation defined by z dz plus w to the square dw plus a function of z w dz. When you have a saddle node, you have one eigenvalues which is non-zero and an invariant curve which is along this direction. And in the zero direction, you have or you have not an invariant curve. Generically, this invariant curve is only formal, but sometimes it is convergent. And it could be good to have a normal form which underline this invariant curve when it does exist. So this is the second part of Ekal theorem. If X has so this second invariant curve is called central manifold. Then one can find such a normal form with f0 equal to 0. This means that in the direction of W, you will here you have the strong invariant manifold in this direction, and in the second one you have an invariant manifold in this normal form if and only if f of 0 equal to 0. So you can find such a normal form if and only if and the analytic invariance of the holonomy map of this central manifold are vanishing for omega in 2I pi n star. So if you consider here the holonomy of the Saddam node, you have a return map phi, which is a tangent to identity map, and there is a theory that you can find in the work of Ekal. There are many invariants for to characterize the conjugacy class of phi, and these invariants appear as a sequence of scalar numbers like this. And in fact, you have a strong restriction if you want to obtain such a normal form for the foliation. You have a strong obstruction which is given by this. This means that almost never, when you have a central manifold, almost never you can find a normal form like this with f of 0 equal to 0. When this is a central manifold, and I consider the holonomy of the central manifold. No, in this case, with those invariants, it is tangent to the identity. Well, I don't want to detail now the statement. It will appear in a more geometrical way at the end of the talk, if I have time. And so, just one word about the proof. It is a direct application of Mould theory. So it is left as an exercise to the reader at the end of the third volume of Les Fonctions Résurgentes. And you need to read first at least the first volume. Okay. So when you want to find normal forms, there is an old idea which I think goes back to the works of Birkhoff, and that was explained to me several years ago by César Camacho. For instance, if you want to prove that a singularity is algebraic, one idea should be to glue this local foliation with other foliation in such a way that you recover P2 with the global foliation. Then automatically the global foliation is algebraic, and you have found a new system of coordinates in which the singularity is algebraic. But this is difficult to do in general. One of the reasons is that there are a lot of singularities which are not algebraic. So I want to do here this construction at least in one direction. I mean that I want to algebraize the foliation in one variable. And those normal forms are like this. All those normal forms are polynomial in W. So I start with a simple case. You consider a foliation in the plane, which is given by a differential form. So consider a germ of foliation. And consider now the vertical line L0. So L0 I assume that L0 is not F invariant. This means that outside the singular point, you have transversality of this line with the foliation on a small neighborhood. Then I want to globalize this foliation. So now I consider that we have, I consider that L0 is a part of P1, and I want to glue this foliation with another one to complete the foliation along P1. So what is easy to do is the following. At the neighborhood of any point, what you can do is to straighten this foliation to the horizontal foliation. You do it by a map phi. You can do it by a map phi which takes the form Z and psi of ZW. This is Fleurbaug's theorem. And I want to do this along a corona. So this is something like W between small r and big R. And I do it in such a way that the restriction of phi to L0 is identity. And here I can complete the foliation until the infinity by putting only the horizontal foliation. When I do this gluing, I find a manifold, a surface. I find a surface equipped with a rational curve so in fact I lose this. So doing this together, I obtain a neighborhood of P1 in a surface equipped with a foliation with a singular point and which has no other singular point outside. So now I remark that since I can choose the gluing preserving Z variable, I have also all vertical lines glued together with vertical lines here. So here I have not only a neighborhood of P1 but a P1 bundle. So this manifold M is in fact something like the disk times P1. And by this way, the foliation here becomes algebraic in the variable W. In fact, you can write down in new coordinates here. I fix new coordinates that I still call ZW. And in those coordinates, the foliation is defined by a differential equation of this form with here a unique meromorphic function which in restriction to each fiber is in fact a rational function. So this is W rational function. So what about the degree of this function in W? I go back here and I said that L0 is not F invariant. This means that G of 0W is not identically vanishing. So you can consider the order of this function at 0, denote this K. In fact, the zeros of G of ZW are exactly coincide to the curve where the foliation has a vertical tangency, a tangency with a vertical fibration. And K is just the number of intersection of this curve that I will call sigma, of this curve with a generic fiber. So sigma is the tangency set between F and the vertical fibration. And if you look at this point of view, perhaps it is more easier to do with this. You look at the vector field, which also define the foliation. The poles of here, of R, the poles of R are exactly coincide with this set sigma. So this set sigma is also here, and the poles of R coincide with sigma. So if you look at this vector field, when you fix an horizontal coordinate, you look at the fiber, you have here a vector field on P1, which has exactly k poles, and thus k plus 2 zeros. So you can specify this function now. So this function is something like this. You have a Weierstrass polynomial of degree k plus 2 over another Weierstrass polynomial of degree k. So you have this preliminary normal form, and here you have to choose two things. You have to choose the horizontal coordinate. So this is up, this normal form is up to the choice of the horizontal coordinate. You can look at this kind of transformation, a permutation of the fiber, and automorphism of the fibers, which are of the form W to alpha of Z W plus beta of Z, gamma of Z W plus delta of Z. So immediately what I do is the following. I take one leaf here and I straighten it to the infinity by using a Möbius transformation. And moreover, so this means that so instead of this, when you straighten a leaf to the infinity, you can remark that you have now a degree k plus 1 Weierstrass polynomial. And this is now up to an affine transformation. And then you can do a little bit more. You can straighten at the order 2 this leaf by using linear transformation. I mean that you can, after this leaf has a contact of order 2, the horizontal foliation has a contact of order 2 with the foliation f. And by this way, you have here k. And this is up to those two possible transformations. In fact, all of this can be done for not for the dimension 2, but for foliation in dimension, in higher dimension, in Cn plus 1. So here you just have the sum of Fe dZe, and you can do the same. You need here that it is a foliation. This means that you have integrability condition. And you can repeat the same thing. You have vertical fibers which are P1, and the leaves are n-dimensional. You can also straighten the leaf, one leaf at infinity. And what you find here is not a rational function, but a one form which is rational, which has rational coefficient in W. And you obtain the following theorem. So let omega one form in Cn plus 1, satisfying the integrability condition, assume that, so I had the condition that the line is not invariant. Up to a rotation, this means that the foliation is not tangent to the radial vector field. So I consider the radial vector field, and I look at omega taken to the radial vector field. This is a function, and I can look at the order at 0 of this function. And I assume that this is an integer which is less than the infinity. Then this construction provides the following normal form. F is, the foliation is analytically equivalent to the following form: omega 0 plus omega 1 W plus, and so on until omega k W to the k plus a Weierstrass polynomial of degree k dW. But I forgot to say here, in Cn plus 1, Z is equal to Z1, Zn. And these are one forms in the Z variable. And this is a Weierstrass polynomial. Of degree k.
You mean the omega I depends only on dzi?
Yes. So it looks like a preparation theorem, and in fact you can do the same for a function. If the foliation is induced by a function, you start the same construction, but keeping in mind that here you have a function defining the foliation. Then you have a preliminary step to do, which is the following. So you start with a function, and you consider, for instance, omega equal to df. And then you look at the restriction of f to L0. This is a germ of function in one variable, and f to the L0 is equivalent to some z w to the k. So in fact, you do this preliminary change of coordinates here, so that the restriction of the function to L0 is w to the k. Then here you look at you complete with the foliation by the same way, but at the same time you complete with the function w to the k. And this gluing will glue at the same time the functions. And here you have not only a foliation, but a foliation defined by a global function. Here you have the pole of w to the k at infinity, the polar set of the function. You put it at infinity so that this function is a polynomial. And you find a Weierstrass polynomial. So you have this, you consider a germ of function of Cn plus 1, 0, 2, C0. Assume, as for preparation theorem, that K, which is the order at 0 of f of 0 w, is less than the infinity, then f is analytically equivalent as a function to a Weierstrass polynomial of degree k, unitary Weierstrass polynomial. So this can be done also for meromorphic functions, germ of meromorphic functions. You have a quotient of two Weierstrass polynomial. And also you can do this for closed one form, and you have a normal form for the closed one forms. How much time? Okay, now I consider the case where the sigma is smooth. This occurs where, more precisely, the case k equal to 1. In the case k equal to 1, so sigma is smooth, and also it is transversal. It is transversal to L0. Then you can use the further change of coordinate here to straighten sigma on w equal to 0. So so what does this mean for this theorem? So for this normal form, you have k equal to 1. So here I write this normal form in more detail. You have omega 0, omega 1 w plus g0 of z plus g1 of zw dw. In fact, okay. So here I assume that k equal to 1. In fact, you can look at the linear part of omega, and this condition is like this. Omega 1 taken onto the radial vector field is different from 0.
It's not the same omega. Oméga 0 plus oméga W.
So,
En bas. Il y a deux oméga.
Okay. Yes.
Sorry. With the vector field or with the vector field tangent to the vector?
No, radial. Because if you have, if it is not zero, then up to rotation, you can find you can assume that the vertical line is not invariant. Okay.
But because when you say that it always has order of tangent to 0, at least 2. Omega 1 is a quadratic polynomial.
Yes, I have. So it was k plus 1 before. It was k plus 1. Sorry. Okay, so in this case, if the linear part is not tangent to the radial vector field, then you have this normal form. In fact, because k is equal to 1, it is easy to verify that this is not vanishing, so you can divide by this coefficient. And when you have straightened sigma onto W equal to 0, you have only, you have killed this coefficient. So now you have this normal form, like this. And now you can use the fact that this one form is integrable. So integrability condition gives you the following, that d of omega tilde 0 equal to d of omega tilde 1 equal to omega tilde 0 omega tilde 1 equal to 0. This means that in fact these two holomorphic one forms are exact. So modified here, you have two functions. And this condition means that those two functions are define the same foliation. So you can apply the theorem of Mattei-Moussu. And in fact, there is a function h of z which factorized the two functions here. So Fe is equal to a function of this one, h. It is something which goes from Cn, 0, to C0. Several remarks about this result. The first one is that this result was obtained for n equal 2. It was obtained formally by a formal change of coordinate by Dufour and Zitomirsky. They were dealing with Poisson structure, and they had a formal normal form theorem on Poisson structure, and by a correspondence between Poisson structure and foliation, they deduced this form, this normal form. But it was only formal. 2 for n equal 1, so in the plane, this is the orbital part of Strozina-Zoládek. In the plane, this is the normal form of Bogdanov-Takens for the foliation, not for the vector field, but for the foliation. a third remark. Yes. If you look in the variable w tilde equal to 1 over w, you find the following. So I write, as before, omega tilde 0 plus, so you find this omega 1 w to the square minus d w tilde. You find this equation, which is an ordinary differential equation in the sense of Servo. That means that this means that the length of the foliation with regard to the God-Bienve sequence, the length of the foliation is less or equal to 3. Fourth remark, also in the spirit of the previous talk, in fact this foliation comes from a foliation in dimension 2, whatever is the dimension here. Because of this map H, you have, if you consider the change, the map given by by H and W, so this is a map from Cn plus 1, 0 to C2, 0, and the foliation, in fact, comes from a foliation in normal form in dimension 2. It is a pullback by an holomorphic map of foliation in dimension 2. So now if I want to prove the theorem of Strozina-Zoladek for vector field, I just have to adapt this proof. So now I go back to vector field. And this proof immediately adapt to this case in the following way. So you start with a vector field X. You consider its linear part. So you are here in C2, 0. And the linear part, so I assume I don't need that the vector field is nilpotent. I need that the linear part is not radial. Assume that x1 is not tangent to the radial vector field. So in a convenient coordinate, x1 can be written in the following form: 0, 1, alpha, beta. You have the product of the eigenvalues and the sum of the eigenvalues. In fact, if you look at the eigenvalues lambda I, the eigenvector is given by 1 lambda I. So the invariant curve in general are, for instance, for a saddle, the invariant curves are like this, and you have the tangency set here. So now I consider this with equipped with a vector field. So I have only to do a preliminary transformation, like for function before, by a change of W coordinate, which is tangent to identity. I can put, I can assume that, so X is given by f dz plus g dw, I can assume that f of 0w is exactly equal to w. So at the linear part is given by w because of this matrix. I assume that in restriction to L0 it is really w. So in restriction to L0, L to L0 is exactly w dz. Well, and I will glue this vector field with the vector field w dz here. Unfortunately, if I want to preserve the vector field, I can no more assume, moreover, that I have the identity here. In fact, when I glue, I lose the vertical fiber. I have no more vertical fiber at the end of the construction. So here there is a small computation. So here you have a phi of z w. So I can keep the condition that phi restricted to L0 is identity. But if you compute, you see that the Jacobian of phi is of the form 1, 0, something, 1, all along L0. This is due to the preliminary normalization here. And therefore, this means that at least the P1 here has 0 self-intersection. So you have M, and here you have L0 isomorphic to P1 with 0 self-intersection. Then if you look at the very recent paper of Camacho with Morazzotti at the end of this book, you find a reference to a work of V.I. Savelev. In fact, this implies that M is isomorphic, is still isomorphic to the trivial bundle, the disk time P1. As a germ. So it is up to restricting the tubular neighborhood. And so after, this works as well. So what you have to do, you have to consider the pole of this vector field at infinity. You straighten it doubly here to the infinity. And after, you have to straighten sigma, the tangency locus. And if you look at what does this mean for the vector field, you obtain the theorem of Strozina-Zoladek, but you obtain this for all simple singularities. So theorem 2, if x is like this, x1 not tangent to the radial vector field. In the radial case, you have Poincaré theorem. Then x is analytically conjugated to the Bogdanov-Takens normal form that I rewrite here. Thank you very much.
C'est de la magie, hein. C'est de la magie.